Here, we'll look more in depth at the physical properties of vascular resistance and how it affects pressure and flow. Poissier was a French physician who studied hemodynamics in the 1800s, and Poissier's law describes resistance in fluid systems. So this law describes the laminar flow of a viscous liquid like blood through a cylindrical tube like blood vessels. And the resistance is the result of friction caused by the interaction between these adjacent layers of fluid in laminar flow. So the movement of fluid is driven by a given pressure, this P1, across the length of this tube here, which offers some resistance. And the fluid flows across this resistance, and the pressure is dissipated as it flows through the tube according to the level of the resistance present in the tube. And then at this ending pressure, P2, it's less than the original starting pressure. So there's a pressure drop as the fluid flows across the tube that's proportional to the level of resistance. The forces that give rise to the resistance in the tube are shear forces that happen because of the interaction between the layers of laminar flow. So as the flow starts here, driven by this pressure P1, an infinite number of layers of flow starts to develop, and that's the laminar flow. These different layers have different velocities, where the center layers furthest away from the walls of the tube are flowing the fastest because their resistance is the smallest. And the resistance in that tube, we said, is created by shear forces between these adjacent layers and the shear force between the wall of the tube and the layer closest to the wall. Now let's take a look at all the factors that influence the resistance in the tube. And all of these factors relate to the creation of that laminar flow and those shear forces we just talked about. So the first factor we'll look at that influences resistance is the length of the tube that the fluid's flowing down. And if that length is increased, then there's a longer time for those shear forces to act, which leads to a higher resistance to flow. Of course, in the body, the length of the blood vessels is anatomically set and is not physiologically regulated. The next factor we'll look at is viscosity, or how thick the fluid is. So increasing the viscosity increases the resistance because there's more shear forces between those layers of fluid. So in the body, the blood viscosity is determined by the hematocrit. The greater the proportion of blood that's made up of red blood cells, the greater the viscosity of that blood and the more resistance is present. And finally, the most important factor by far is the radius of the tube or the vessel. And this is because, as we said, the greatest shear forces develop between the walls of the vessel and the fluid. So here we see that the radius to the fourth power is inversely proportional to the resistance. So that means the greater the radius is, or the larger the vessel, the smaller the resistance is. And that's determined by this factor of 4. So if you were to increase the radius by a factor of 2, you'd actually decrease the resistance by a factor of 16. So this is a really powerful relationship and a very effective way to regulate resistance in blood vessels. And finally, this 8 over pi is a constant. So the location of resistances with respect to other resistors is also important in the cardiovascular system. And in a set of vessels arranged like in a series like this, blood flows sequentially from one vessel to the next. All of the fluid has to flow through each of these 3 segments. And just like resistors in electrical circuits, resistors in fluid circuits summate when they're in series like this, with one after the other. So the total resistance of this series of 3 resistors is just the sum of the resistance of each individual segment. So in other words, the pressure drop across this entire system, or the difference between the pressure going in and the pressure coming out, is the sum of the pressure drops across each of the individual resistances in the system. So this means that the total resistance of the series must be greater than the resistance of any individual component or any individual segment. And changing the resistance of any single segment produces a proportional change in the total resistance of that circuit and to the pressure at any single point. And the systemic circulation is an example of blood vessels in series. So here, at steady state condition, the cardiac output of the left ventricle is equal to the venous return to the right atrium, which is equal to the cardiac output of the right ventricle, which is equal to the venous return to the left atrium. So we can group vessels together and consider this to be a system arranged in series. And here, if we just group all of the systemic arteries together, that's one resistor, all of the arterioles together, that's the next resistor. We group all of the capillaries together, that's the next resistor, and so on. And so to get the total resistance of the series, you just add the resistance of each of these groups of vessels. So this is an example of physiological resistors in series. There are also resistors in parallel in the cardiovascular system, and blood vessels in parallel are arranged in branches like this. So here, the reciprocal of the total resistance is equal to the sum of the reciprocal of the resistances of each individual segment. In this case, the total resistance is less than the resistance of each individual segment. So in other words, any of the resistors found in the parallel system actually have a greater resistance than the total resistance. So that means that R1 is greater than RT, R2 is greater than RT, and R3 is greater than RT. So this is interesting and important in the cardiovascular system because in this type of arrangement, a change in any one resistance of one of these segments greatly affects blood flow in that individual segment, but actually has a very small effect on the total circuit resistance and pressure at this point A. Another interesting thing about this arrangement is that increasing the resistance of a resistor in parallel can then cause shunting of blood to other areas. So, for example, R3 has the smallest radius in this example and therefore the highest resistance. So the lowest amount of blood will flow here, while the greatest amount of blood will flow to the area with the least resistance down here in the bottom segment R1. And all of the major arteries that branch off of the aorta is one example of vessels arranged in parallel. So in this system, blood flows through the aorta, and then it separates and it's distributed among the different organ systems, with some blood flowing to each of these circulations, whether it be cerebral or coronary, skeletal muscle, or any other organ or tissue. And in this parallel arrangement, there's no loss of pressure. So the mean pressure in each of the major arteries to these organs and tissues is approximately the same as this mean pressure in the aorta. We also know that it's possible to shift the blood flow from one organ to another organ system just by changing the resistance of one of these individual circulations. And that change in the individual circulation doesn't change the overall resistance of the system by a large amount. So this is how the body is able to actually redirect blood to where it's needed most without having a big effect on the mean arterial pressure.